done balancing equations and starting to classify them. We will classify them more as we go. But we're going to look at atoms, moles, and molecular formula weight determination. Okay? Now, by definition, one mole is the number of particles found in 12 AMUs of C12. So 1 mole of an element has the mass in grams equal to its atomic weight. So if you say a carbon atom is 12.01 AMUs, atomic mass units, then that means that 1 mole is equal to 12.01 grams of carbon. So all it is a counting number. Now, it's a counting number that you need to know. You may have encountered it before. It's 6.022 is the form that I'm going to use. So it's 4 significant digits. And be aware that most calculators have constants built into it, and Avogadro's number is one of the constants that is built in. However, you need to check and make sure it has the same number of digits, because if you use it and it's only 6.0, then you're going to get wrong numbers. If it's more than that, that's fine. You can use significant figures to make it come back. But bottom line is I'm not going to give you this value, so you need to learn it. Also, you'll need to learn how to put it into your calculator correctly. Okay? So let's talk about atomic weight. It's the mass of 1 mole of that element given any species. Now, the mass I gave you for carbon 12 before was 12.011 grams per mole. That is what you see on the periodic table because it is a weighted average. Remember, we did that. It is a weighted average because it includes all of the species, the isotopes associated with it. So when you look at a compound, so if we look at 1 mole of potassium, that's actually 6.02 times 10 to the 23rd potassium atoms, which means that it's 39.10 grams per mole. And again, remember, the molecular weight is going to vary slightly based upon which periodic table you use, which is why I am posting the Van somebody's periodic table, and that is the one that I expect you to use on all work you do for me so that we have consistent numbers. Okay, and so I'm going to use it when I do it, so significant figures will usually be based upon, usually not on periodic table numbers, but if you use one that uses smaller numbers, then yes, it will get you into trouble. All right, so nitrogen, N2, it's a diatomic, remember that. So it's found naturally as N2. So it actually contains double the amount of nitrogen atoms, and the weight is 2 times the 1 nitrogen because the elemental form of it is the diatomic. So the point of that is you have to be very careful when you're working problems so that you can know whether it's a diatomic or not. Now, that's the atomic mass. If we look at the molar mass, it is still the mass of 1 mole of that substance. And again, we're still using the carbon 12. However, if we look down here at carbon monoxide, then 1 mole of carbon monoxide contains 6.02 times 10 to the 23rd carbon monoxide molecules, which has this mass here. And if you take it apart, then it has 6.022 times 10 to the 23rd carbon atoms combined in it. And the same thing, remember that's your ditto mark, which means the same thing as oxygen atoms. So in this case, since they're 1 to 1, then you have the exact same number of atoms as you do in the molecules, etc. In the case of water, this is not true because hydrogen is 2 for every 1 oxygen. So you still have 1 mole of oxygen molecules, which has the mass of combining 2 hydrogen plus 1 oxygen. But if you take it apart, we have double the amount of the hydrogen atoms to 1 mole of the oxygen atoms, which is where we get our total mass. When we add it together, we'll get the 8.02, and that's using the significant figures. But that's how you get your masses, and you've got to look at it in combination of how many atoms of each compound you have. Now, that is molar mass. Molar mass is the same thing as molecular weight. They are used interchangeably. It's the mass of 1 mole or the molecular mass, and it's the sum of the masses of all the atoms present. So if you have, present in the molecule, and so if you have 1 carbon or 2 carbons and 4 oxygens, then you would add them all up. Okay? Now, formula mass is the sum of the masses of all atoms present again. But in the first one, this is in the molecule. Formula mass, and we do use them interchangeable, is the formal unit. And what's a formal unit? Well, basically, that's what we call the formula of an ionic compound. So in this text, especially, they use molecular mass and formula mass interchangeably. And most of the time I'm going to do so well, but technically they're not the same thing. If it's an ionic compound, you call it the formula mass. If it's a molecular compound, you call it the molecular mass. And remember, mass and weight, because we're operating on this planet, are used interchangeably. So again, molar mass, molar weight, molecular mass, molecular weight, formula mass, formula weight, are mass and weight are interchangeable. Now, the only trick is remember that when you're doing equations, don't forget to look at diatomics and other oddities when you're doing equations, because remember, oxygen single is not equal to oxygen diatomic. Okay, so let's work some problems. So we're going to calculate the mass of heptanoic acid. Now, if you're given a compound, you have to come up with a formula, but in this case, I'm not expecting you to know what heptanoic acid is, so therefore, I'm going to give you the formula. So what we're going to do is we're going to look at it and we're going to count. We have 1 carbon here. We have 5 carbons here because we have this outside the parentheses, and we have 1 carbon here. So we have a total of 7 carbons. We're going to count hydrogens. We have 3 here, we have 10 here, and we have 1 here. So that's 14 hydrogens. And then we have 2 oxygens. Okay, so if we look at our periodic table, that's 7 times 12.011 grams per mole. And 14 times 1.008 grams per mole. And these are 2 oxygens. 2 times 15.994 grams per mole. And so we would total that together and we find out we have 130. Whoops. Let me erase that stray mark. So let's just erase the whole thing. So 130.1878 grams per mole. Now, in this particular case, we have 4 digits would be the last 3 places after the decimal. My recommendation is that you keep, and when you would add them all together, that's what you would use, is the 3. So you could technically report it as 188 because you've added it together. But usually you have so many digits on atomic masses that you don't want to use those as significant figures. So that's the first one we have. This one is a mass of cobalt 3 sulfate. Well, what that means is cobalt is 3 plus, and we know that sulfate is SO4 2 minus because we memorized those. So when we combine them, we're going to multiply this one by 2 and this one by 3. So we're going to get cobalt 2 SO4 3. So what that means is we're going to have 2 cobalts, 3 sulfurs, and 12 oxygens. So again, if we look it up, that's 2 times 58.9332 grams per mole. Sulfur is 3 times 32.066 grams per mole. And oxygen is 12 times 15.9994. And remember, you want to use whatever is on the periodic table. So we end up with a value of 406.0572 grams per mole. If you did not use the periodic table that I gave you and you're using a different one, that's okay for a lot of things, but when it comes to the test, that's what I'm using, so that's where the significant figures come out. So if your number varies slightly, that's fine, as long as it's lower down in the significant figures. Okay, this again brings you to Chemistry and Life, one of these little lanyap. This one has to do with the glucose monitoring. And this brings us back to conversions, because what we've been doing is we've done the molecular weight, but before that we did moles. So what we're moving between is atoms and moles and the mass, okay? And the mass comes from molecular weight. So these conversions, there is no direct conversion between mass and atoms. That one doesn't exist, so you have to go steps. So if you look at it, when we go start with grams of A, whatever compound A is, we use the atomic weight, assuming it's an elemental. If it's a molecule, then we would use the molecular weight. But so the atomic weight is grams per mole. And again, it's like a dozen. 1 dozen is equal to 12 items. You can say it that way, or you can say 12 items is equal to 1 dozen. As long as you keep 12 with the items and the 1 with the dozen, we can go either way. So for example, to go from grams to moles, we use the atomic weight with the mole with the grams on the bottom because we're canceling unit. Here we need to cancel our moles, so we're going to put the moles on the bottom and the grams on the top. So that'll allow us to get to moles to gram. If we're going for atoms, then if we start with moles, we use Avogadro's number, and again, we need the moles on the bottom for the atoms on top to give us the atoms that we need. If you're starting with atoms and going to moles, then if you'll notice, the atoms are on the bottom. And again, you can flip this either way as long as you keep Avogadro's number, 6.022 times 10 to the 23rd, with the atoms. Okay? So we're back to the units that we talked about before. It doesn't matter if you know what you're doing, as long as you keep your units straight. You will get where you need to go by following, because here we have the grams canceling with grams and we're left with moles. Moles cancel here, we're left with grams. We can do grams, one step to moles, to atoms, or we can start with our atoms, cancel our atoms, moles cancel, and we're left with grams. So notice that each, what we start with, we've got to get rid of using a conversion. Okay? So we're going to work these. How many moles of platinum are in a 1.25 gram sample? So I always start with what I'm looking for, moles of platinum, because I tend to get lost if it gets more complicated. 1.25 grams of platinum. And if we look on the periodic table, we find out that there are 195.078 grams of platinum per 1 mole of platinum. And that gives us 0.00640769933 moles. But if we go back, we have 3 significant figures here, and we have 6 significant figures here. So we would report it in the least. So we're going to report it in 3 significant figures. So it'd be 0.00641 moles. And remember, the first 2 zeros here are placers. And with the 0 after the 4, you look at the following number, which is the 7, so you'd round up. Now, if you prefer to do it in scientific notation, there's your 3 significant figures, and you could use it times 10 to the minus 3. As I said, some people really love scientific notation, some people don't. So, tomato, tomato, don't care which ones you use as long as you specify your significant figures. Okay, how many atoms are there in the platinum sample? Now, I'm going to tell you that, yes, you could use the previous number you've generated, but I prefer you don't, because just in case you made a typo or you put numbers into your calculator wrong, which happens all the time. I do it, you do it, it just is. If you start over and don't use a previous answer, and you're going to have to use the previous answer in a variety of places coming up, but if you don't have to, don't. Okay? So we're going to again go back to 125 grams of platinum, and we use the same molecular weight, and when in doubt, you can look it up per 1 mole. And so now our grams are gone. So we're left with moles, and we know that 1 mole of platinum is 6.022. Whoops. I can say it, but obviously I can't write it. Times 10 to the 23rd platinum atoms. And that's equal to 3.8587. 129 times 10 to the 21. So if we look at it, we have 3 significant figures. We're back to 6 significant figures. Avogadro's number is 4 significant figures, so we're going to report it as 3 significant figures. So it's 3.86 times 10 to the 21. Now, you don't have to use scientific notation here, but I don't want to count that many zeros. Okay, so this is my final answer. Now, a couple of statements that I want to make is, remember, it's a good idea to write both this number and the final number, because that'll tell me that A, you can do your math, and this tells me that you can do your significant figures and partial credit rules. The other thing is, remember, anything on top is multiplied, anything on the bottom is divided. And you can do it in any order you want, as long as you don't miss things as you go. All right? We're going to work one more set. And we're going to look here at going the opposite way. So this one is, how many moles of tin are there in a sample containing that many 10 atoms? So again, you're going to start with the amount you're given. In this case, it is that many atoms, and we need to get rid of our atoms, so atoms are going to go on the bottom. So what we have with atoms is Avogadro's number. There are 6.022 times 10 to the 23rd 10 atoms for every 1 mole of tin. Oh, and we're stopping here for this one. So if we look at it, that gives us 14.051810 moles. And I'm not sure I stated it before, but the mole is just a counting number. It's like the dozen of chemistry. Okay, and again, we're back to significant figures. So we have 4 significant figures here, 4 significant figures here. So I'm going to report it in 4 sig figs, which is 14.05 moles. Now, on the second part is we're going to grams of tin. So again, we're going to start with our number. And again, I'm looking actually at the problem, not what I wrote before, in case I wrote it wrong. And trust me, we all sometimes have dyslexic moments, some of us more than others, but it doesn't matter. We all have them. I can't talk and write sometimes simultaneously, and sometimes math is optional. Okay, so we have 10 atoms here, so we have 6.022 times 10 to the 23rd 10 atoms is equal to 1 mole of 10. So if you'll notice, my atoms are gone and I got my moles, but I want grams, so my moles have to go in the bottom. And I know that 1 mole of 10, and I go look it up on the periodic table because we're dealing with elementals, is that many grams of 10. So when we work it out, we get 1068. See, I told you I couldn't talk and write. 0.90369 grams. If we look at it, we have 4 significant figures here, 4 significant figures here, 6 significant figures here. So we're going to report it as 4 significant figures, which means we have 1668 grams of 10. Okay. So these are elemental. We've determined molecular weights, but that's all we've done. We will do more with molecular weights as we get to stoichiometry. And this stops the part of chapter 3 that will be on the first test. So anything after this one will be on the next test.